Hello everyone, my name is Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams. And this video is going to focus on how we tackle equilibrium calculations. So when a reaction is in equilibrium, you've got the forward reaction, you've got the reverse reaction. It appears that the reaction has stopped, but actually what's happened is the rate of the forward reaction equals the rate of the reverse reaction. And typically on an exam question, what you get given is the initial number of moles and then the equilibrium number of moles of one of either the reactants or the products, and you have to do a calculation to work out the equilibrium moles of all of the reactants and products, and then you can calculate your value for Kc. So if you haven't seen any of the other videos on equilibrium, you might want to pause and watch those first. This video is going to tackle more of the A2 style calculations, so ICE tables, initial, change and equilibrium. And as always, if you find this video helpful, please like, please subscribe, please share with your friends, please keep checking back for more content. And what I'm going to do in this video is focus on two specific examples. So you might want to pause the video, have a go at the question first, then work it through with me as I go through it. Or if you don't know what you're doing, you might just want to watch it through first. Okay, so you've got this equilibrium here between a carboxylic acid and an alcohol producing an ester and water. And the first thing you have to do before you do anything else is to write an equilibrium constant for Kc and give the units for it. So Kc is always the products divided by the reactants. So the products would be the CH3, COOCH3. Because it's Kc, it needs to be square brackets, concentration, times the concentration of the water, and then divide that by the reactants. So that's the carboxylic acid times the methanol. So that would get you one of the 2 marks. You then have to state the units. Well, concentration is moles per dm cubed, but there are 2 lots of concentration on the top and 2 on the bottom, so that just cancels down to no units. So that's the first bit. You had to write an expression for the equilibrium constant Kc. Calculate the number of moles of ethanoic acid present at equilibrium. Well, to do this, we need to use some of the data from the question. It tells you that you've got 32 centimeters cubed of 1.25 moles per dm cubed sodium hydroxide. So let's start off by working out the moles of the sodium hydroxide. So moles of NaOH. And that's equal to the concentration, which is 1.25, times the volume, which is 32. Divide that by 1,000. So that comes out as 0.04 moles of sodium hydroxide. And sodium hydroxide, NaOH, reacts with the ethanoic acid, CH3COOH, to form water and sodium ethanoate. So therefore, the moles of the sodium hydroxide must equal the moles of the ethanoic acid at equilibrium. So you must have 0.04 moles of ethanoic acid at equilibrium. Okay, so to tackle the rest of the problem, we need to make an ICE table now. So I'll show you what I mean by that. You've got the acid in the first column, which is your carboxylic acid. You've got the alcohol. Then you've got the ester. And then you've got the water. So those are the 4 things that are involved in the reaction. Make a table then. The first row will be I, which stands for the initial number of moles. The initial number of moles of each. So the initial moles of the acid was 0.1, and it was reacted with 0.083 moles of the alcohol. And technically, by definition, the moles of the ester and the moles of the water would be 0 to start off with because they haven't had any time to form yet. So that's your first row. C stands for change. We'll come back to that. And E stands for the equilibrium number of moles. Now we know from the calculation that we've just done previously that the equilibrium moles of the acid is 0.04. So therefore we're in a position now where we can work out everything else. If the acid was 0.1 originally and it ends up at 0.04, the change is 0.06. Let's put this in a different colour. It must have gone down by 0.06 moles. And therefore the alcohol must have gone down by 0.06 moles because they react together in a 1-to-1 ratio. And the ester and the water must have gone up by 0.06 moles because they are products. So now we can work out all the other equilibrium moles. So the moles of the alcohol at equilibrium must be 0.023. And then the ester and the water must both be 0.06. So once you've worked out all your equilibrium number of moles, we're not told the volume of the container here, so we're just going to assume that these moles are the same as moles per dm cubed. So we then plug our numbers into the Kc expression that we created on the previous slide. So Kc would be the number of moles of the ester, which is 0.06, times the moles of the water, 0.06, divided by the moles of the acid, which is 0.04, times the moles of the alcohol, which is 0.023. And that gives you a value of 3.91. No units, remember. Now, it's worth commenting at this stage on what that number actually means. There are 3 scenarios, really, for Kc that we need to be aware of. Kc being greater than 1, Kc equals 1, and Kc being less than 1. Now when Kc is greater than 1, so this scenario here, if we think of how Kc is calculated, it's products divided by reactants, that means there must be more products dominant in the equilibrium, so the products dominate. Equilibrium lies to the right-hand side, and the bigger the value of Kc, the more the equilibrium lies to the right-hand side. However, when Kc equals 1, this scenario here, the concentration of the products and the reactants must equal each other. Whereas if Kc is less than 1, the last scenario here, then there must be more reactants than products. The bottom half of this equation must dominate, so equilibrium lies to the left-hand side. So it's always worth being aware of what your number means when you calculate it. And then it also says, state giving a reason what happens to the value of the equilibrium Kc if the temperature is increased. Well, it tells you in the question that delta H is -3 kilojoules per mole. So that means the forward reaction is exothermic. Now, exothermic reactions prefer low temperatures because they just dissipate the heat anyway. So if you increase the temperature, it's actually going to shift equilibrium to the left-hand side, to the endothermic direction, and actually your value of Kc would decrease. So for an exothermic reaction, if you increase the temperature, it'll shift equilibrium to the left and your value of Kc would decrease. Okay, so here we've got another example that's going to need an ice table. The only difference that makes this a bit more challenging is that the ratio in the balanced equation isn't 1-to-1 anymore, it's a 1-to-3-to-2. So we're going to have to factor that in, firstly in our Kc expression, but also in our ice table as well. But once we get into the principle of how to do it, it's relatively logical. So remember that Kc is products divided by reactants. So it's the concentration of the ammonia, and that needs to be squared because there are 2 moles of ammonia. And then you divide by the concentration of the nitrogen. Technically that's to the power of 1, but we don't need to bother with that. And that's times the concentration of the hydrogen, and that's cubed. In terms of units, you've got 2 lots of concentration on the top and 4 lots of concentration on the bottom. So that's what it looks like with 2 on the top and 4 on the bottom. You wouldn't get any marks for that. You'd need to simplify that down. So the moles cancel down, and the dm to the minus 3 cancel down, and then you repeat, which leaves you with this, moles per dm cubed twice on the bottom. Now technically, this is moles squared on the bottom. Bring it to the top and it becomes moles to the minus 2. And then you've got dm to the minus 6 on the bottom. Bring that to the top and it becomes dm to the plus 6. So your answer for the units would be moles to the minus 2, dm to the plus 6. Okay, so now we've got an equilibrium expression. We need to do an ice table, same as before. So your first column, nitrogen. Second column, 3 lots of hydrogen. And then 2 lots of NH3. And then your first row is I, where I is the initial moles before equilibrium is reached. C is for the change. And E is for the equilibrium number of moles. So it tells you in the question that you've got 3 moles of nitrogen gas and 1 mole of hydrogen gas are combined in a 1 litre reaction vessel. The size of the vessel is important because if it was 2 litres, you'd need to work out the number of moles in 1 litre because it's moles per decimetre cubed. But because it's 1 litre, it's nice and straightforward. So you've got 3 moles of nitrogen, 1 mole of hydrogen, and by definition there would be 0 ammonia initially because it's a product, it hasn't had time to form. And it tells you at equilibrium 0.663 moles of the hydrogen remain. What are the resulting concentrations? Well, start off by working out the change in the hydrogen. So it's 1 minus 0.663, which is 0.337. It's gone down by. Now the nitrogen, because it's a reactant, must also have gone down. It's got used up, and it must have gone down by 1/3 the amount that the hydrogen has gone down, because of the ratio in the equation. So it must have gone down by 0.112. And the ammonia must have gone up, and it must have gone up by twice the amount that the nitrogen has gone down, because it's a 1:2 ratio. So it must have gone up by 0.224. So that's your changes taken care of. And therefore 3 minus 0.112 is 2.888. And the ammonia must be 0.224. Once you're through to this stage, you've done the hard work. We just need to plug it back into our Kc expression that we looked at on the previous page. So it's going to be the concentration of the ammonia squared. So it'll be 0.224 squared divided by the 2.888 times the 0.663, but that needs to be cubed. And altogether that comes out as 0.0596. And remember that had units of moles to the minus 2, dm to the plus 6. Well, thank you for taking the time to watch this video. I hope it was helpful. If it was, remember to like, subscribe, keep checking back for more content as I'll be adding it all the time. Thanks everyone, see you next time.